Grade 9 math, lesson 4.5, using graphs to estimate values. So graphs are really useful to give information out about what's going on. So what we got here is we have population and water usage, right? And you can think about this. If the population increases, should we be using more water? Well, of course. So these are usage in mLs, which is 1 million liters, right? So we use that to represent this so we don't have to write a lot of zeros when we do this. So we can graph this out. So dependent, independent, right? You have no control over the population, and the amount of water they use depends upon the population. So we can graph this out, population along the bottom, water usage along the top, and we can see that it's a nice line here. So let's produce some predictions. Estimate the monthly water usage for a population of 150,000 people. So 150,000 people would be halfway between 100,000 and 200,000. So then we just do a vertical line straight up until we hit the line. Bang, we come across, and you estimate as best you can, about 1,100 mLs. And again, your answers could vary, right? You could have like 1050 to maybe 1200. Like there's a range of values here for this one. Okay, so we can do this the other way around. Estimate the population when the monthly water usage is 1,400 mL. So where's 1,400? Yeah, it's about approximately there. Horizontal line straight across until you hit the line, and then vertical line down. Yeah, about 185,000. You could have a range again, maybe 180,000 to 190, whatever you want to do with that one. Okay, now the problem with this next part is, what happens if it's 250,000 people? Well, I don't see that on the graph. Well, what we can do is we can extend the lines if we need to over this value. So it would be somewhere like way out here, but that's not part of the graph. Well, okay, we're coming to that. Go to the next page, and let's look at this one here. So what we have is a graph shows the distance traveled by a car on a highway over a 4-hour period. So time is along the bottom here, and the distance goes up here. So what we can do is we can ask, hey, what's the distance traveled at 2.5 hours? So 2.5 hours would be here. We go up and we come across. Yeah, it's about 200 kilometers. So that's known as interpolation, because what you're doing is you're looking at the data within the graph, right? We're not outside the graph. We're not beyond it up and to the right, like way up here. We're within the graph. So it's interpolation. So you could look, and I could ask you what it is at 1, what it is at 2, what is it 3, what is it 4, or I could ask you distance 300, and you can figure out the hours. But I can't really ask you, hey, what's it at 5 hours or 6 hours or 7 hours? Okay. So that one's pretty straightforward. So again, right, all you do, wherever it happens to be, right, 1.5 hours, bang, you could come across here. So that's about 120 kilometers. If you had like, how long does it take to travel 300? You go 300 across, come down. Yeah, it's 3.75 hours, 3 hours, 45 minutes, whatever you want. But if you look at that, all the information is within the graph. So it's interpolation, right? So that's just a visual image. Okay, now go to the next page. And this is where it gets interesting. Suppose the car maintains the same average speed. And we know in reality that's not going to happen because cars speed up and slow down. But could we predict what it would be 450 kilometers? Well, 450, that works. That's still kind of within the graph. But what about bigger numbers? Like, oh, wow, look way over here. We could graph this. So what we do is we take the linear line and we just extend the line and we just keep going up. And then what we do with the axis, the x-axis, we just keep extending that to the right. And the y-axis, we keep extending that up. So what we can do is we can then predict stuff. And it's called extrapolation. It's like if you want to leave the building, you go through the exit sign. So you're leaving the building. So extrapolation is looking for data that's outside the normal graph. Like you're exiting the data and looking for it. So estimate the time it takes to travel 450. So we extended our graph. We go 450, and then we come straight down. Somewhere over, what, 5.5 hours, somewhere in there? Somewhere around there. Yeah, you can figure it out. So you start with your normal graph and extend all the lines. Extend the x-axis, extend the y-axis, extend the line here, and then you can predict what it would be. So 7 hours if we traveled 7 hours, yeah, maybe somewhere out here. We go up, we go across here, yeah, somewhere between 560 and 580 kilometers. And we could ask 10 hours, 20 hours. You just have to make a bigger graph based on that. Okay, let's go to the next page, and let's talk about Jenna. Jenna's borrowing money from her parents. I think teenagers like to do that. They want some money from their parents. Some parents are pretty good about it, but she's going to pay it back. So what we got here is at 0 time, she has taken from her parents $200. And over the course of 10 weeks, she's going to pay it back every week in increments, right? So you can see it's kind of a block here. It's just a representation. So here, how much did Jenna originally borrow? Yeah, $200. How much money does she still owe after 3 weeks? We go to 3 weeks, vertical line up, horizontal line across. Yeah, she owes 140 bucks still. How many weeks will it take Jenna to repay half the money? So 200, half the money would be 100, whereas 100 right there, we come across, we go straight down. Yeah, 5 weeks, right? You can use graphs to give yourself a lot of information about what's going on. And again, this one is very limited. Like we have a set time frame, 0 to 10 weeks and 0 to $200. So there's really no reason to go outside this graph. Okay, let's look at Maya. Maya jogs on a running track. The graph shows how far she jogs in 10 minutes. So here it is here. There's the graph. But you can see we've already made a mess of this graph by adding all these extra lines. So assume Maya continues to jog at the same average speed. So this red line here, we can just keep continuing up and drawing because it's a continuation. So predict how long it will take Maya to run 2,000 meters. Well, I don't see 2,000 meters on here. So what we do is we continue our scale up the side here. We continue our scale down the X here, and we find 2,000. So 2,000 about there, right? We come across, about 16 to 20 minutes. Oh, sorry, that's the 14-minute one. We got to look at the big. It's the big one out here, the big outside one here, this top one, and then the bottom. Oh boy, that's quite a while. 16 to 20 minutes. Predict how far Maya will run in 14 minutes. Now that's not on here, so 8, 10, right? 12, 14. That's this line here, vertical line straight up, and then horizontal line across. And then you can figure out based on your scale, it's going to take her about 14 minutes. You can go about 1,600 to 1,800 meters. Now, that's assuming she runs at a constant speed. In reality, when you're running, no, you speed up and slow down. So that's a big assumption to make. That allows us to take this line and continue it along. If not, it would speed up and slow down. We wouldn't have a constant speed. Okay, last example here, I think. Yep. So what we can do is we can take a graph sometime and we can look at different values. So determine the value of x when y is 3. So, okay, we got a graph here. It's the red line, and you can see I've already extended it. But here, let's find y equals 3. There's y equals 3. Okay. Now, we don't go right in this case. We go left because we have to. Here's our extended line. We got to go across until we hit that constant line, right? And then we hit it. We come straight down. We found out x is -6. Yeah. So we can predict based on if x, when y is 3, what x is. Now, is that within the graph? No, that's outside the graph. So that's extrapolation. Okay, let's look at the next one here. Determine the value of y when x is 5. Now, x is 5. Oh, yeah, x is 5. Yeah, there we go here. We go vertical this time until we hit the line, come across. That's about 6.5. Now, was that data within the graph? Yeah, that's interpolation, right? Not extrapolation, it's interpolation because it's inside the graph. So think about that. Interpolation is in, extrapolation is outside. But you can change the graph how you want as long as you assume a few things like, constant. So that red line, right? Just keep continuing along. And then you can extend your x and y axis.